Let's get to know a bit about Kubernetes, what its architecture is like, and possibly what are some cool use cases for it. Okay? So, starting with what is Kubernetes, okay? Kubernetes is nothing but a container orchestrator, okay? So it's useful on a situation where you have a bunch of containers up and running and you want some help to manage it. Okay, let's assume, for example, that you have a backend application. You have, I don't know, 10 Docker containers of that application. And how can you efficiently manage those containers running? Okay, how can you make sure that they properly work together? We will see this in a second, but this is what Kubernetes is, okay? This is what it helps us to do. It helps us to orchestrate, let's say, manage all of those containers, okay? Kubernetes is also sometimes referred to as the operating system of the cloud, okay? Because normally today, applications, they are distributed by nature. And because they are distributed by nature, normally they scale horizontally. Okay, if they scale horizontally, this means that you will have multiple instances of a container up and running, which was the scenario I just spoke about. And in this case, Kubernetes can be really handy, okay? It can really help us to properly work with our distributed systems, okay? Now, this is an example scenario of what I was just speaking about. Okay, you have a container, or in this case, two types of containers of app 1 and containers of app 2, and they are up and running, they are running in the wild, and then you can ask yourself, based on this situation, which is a situation we just saw, you can ask yourself a bunch of questions. How will you deal with load balancing between them, okay? So in this case, how will you tell your, let's say, front-end application to which thing you should route to? How will you handle all of the load balancing here? Will you have to do it yourself? Will you do it somewhere? There are questions that can be raised, okay? Also, how can you deal with service discovery, okay? Let's assume that tomorrow someone just starts a new container of app 2. How can I route traffic to that container? Okay, even if I solve the load balancing issue, I still need this new container to be visible to the other ones. So so service discovery needs to be in place, right? And I have a bunch of other considerations that we need to have in consideration, like, scaling. Okay, how will you deal with spikes in traffic? How will you horizontally scale? And also not only the scale out, but also scale in. How will you shrunk the number of running containers? Okay, and also how will you deal with failing containers? Okay, does it make sense to restart? If you want to restart, will you do it manually? Okay, so still some things you have to have in consideration, but also what happens if tomorrow someone does a release, generates a new Docker image version, and how will I solve upgrades or downgrades if something goes wrong with my upgrade? Okay, so there's lots of things, and normally most of them you have to deal with them in a painful way. Okay, you have to do it manually with some manual steps, or reinvent the wheel in order for everything to perfectly work together. Okay, and this is where Kubernetes comes in handy. Okay, Kubernetes has lots of these things built in itself, so that you don't have to build nothing yourself. You just need to pretty much plug and play. You can make use of whatever exists today in Kubernetes. Okay, so it really helps to alleviate the pressure on your side in terms of what you have to do. Okay, now this is a basic architecture of what Kubernetes is. We will see this in more detail in a second, but pretty much normally when you speak about Kubernetes, you speak about a cluster of Kubernetes, okay? And a cluster is nothing but a bunch of machines, okay? In this case, I have here a bunch of nodes, okay? Each node normally, as we know, has a CPU or vCPU and memory, okay? And those nodes, they execute some kind of workload, okay? And we will see in a second how that can be in Kubernetes, but this is normally what a cluster looks like. In this case, as an example, a Kubernetes cluster, okay? And so in case of Kubernetes, each node, as I said, has a specific CPU and memory constraints, which means that whatever I do inside the Kubernetes cluster is bound by the total availability of these nodes. In this case, total hardware availability. As an example, if each one of these nodes has 1 gigabyte of storage, okay, and I want to have a container running here, and that container needs 4 gigabytes, we cannot make this happen because the overall storage of each node is, if we sum it up, is 3 gigabytes, and the container needs 4 gigabytes, okay? So whatever math we do inside the Kubernetes cluster, we always have to have the entire node availability in consideration, okay? Even if it's just memory constraints or CPU constraints, storage constraints, everything when you speak about Kubernetes, normally you speak about the sum of everything, okay? If you have some space maybe available, you can run things, okay? But always, sometimes have all of this in consideration, okay? What is the entire overall availability of the cluster? Of course, this might not be that easy in some occasions, namely when you schedule pods to run, but that's special occasions which we will see in due time when we speak about pods, okay? But the point is, if you try to schedule something in a Kubernetes cluster and you don't have a resource to run the thing you want to schedule, what will happen is that the thing you are trying to schedule will be on a pending state, okay? And then where there's available space, or whenever there's available space, you will be able to schedule the thing you want to schedule, okay? This might sound a bit abstract, but it will be a bit easier once we see some practical examples of this, okay? Moving forward in the Kubernetes cluster, normally those nodes that we saw before, they were generic nodes, but in the case of Kubernetes, we have special nodes. We have a control plane node, okay, which we will see in a second, and we have worker nodes. Okay, here you're seeing that you have 3 worker nodes and 1 control plane. In terms of control plane, normally you just have 1 node executing the control plane, or at least 1 control plane, generally speaking. But in terms of worker nodes, you normally, at least in production, should aim at having at least 3 worker nodes, okay? Just so that you can schedule or at least distribute the scheduling of resources and so on. Okay, and also have fault tolerance and high availability, okay? But as you can see here, the only difference between this one and this one is that the nodes now have a specific role, okay? In this case, a control plane role and a worker node role, which we'll see in a second, and this will make sense, okay? Now, in terms of Kubernetes history, Kubernetes did not start from scratch. Okay, it has a history behind it. It all started in Borg, which was an internal Google project. Okay, it was a bit tied to the Google infrastructure, and over time, this Borg evolved to another Google project called Omega, and then eventually this evolved to Kubernetes, which is a project that belongs to CNCF, okay, Cloud Native Computing Foundation. But the point is, with all this history, okay, starting with Borg and going to Kubernetes, is as you evolve, you become somewhat platform agnostic. Okay, in the beginning, Borg was a bit tied to Google's infrastructure. And as it progressed to Kubernetes, the point was to make it as agnostic as possible of the underlying platform. Okay, now you can have Kubernetes running on Azure or Microsoft infrastructure, AWS, or even your own on-prem solutions. Okay, so as it evolved, it became as platform agnostic as it could. Okay. Now we are going to see in detail, or in a high-level overview, but still with some detail, what a Kubernetes cluster looks like. Okay. Now, this is just a high-level overview of what it is. Okay. We have lots of small pieces here. We will speak about them individually, but my point with this image is to showcase you that Kubernetes is not just a thing. It's a couple of small components that each one of them has their role, okay? And that together, when they work together, they produce this bigger thing that we call Kubernetes, okay? But let's break this small architecture, which we will come at the end again. But let's try to break this down into smaller pieces, okay? The first piece that we can speak about is the control plane, okay? This is one special node that we have seen previously, okay? And it has a bunch of components, okay? But the control plane itself, it's normally regarded as the brains of the Kubernetes cluster, okay? This is where the bulk of the magic is in terms of logic. As an example, it's here that we choose in which of the worker nodes actually work will be executed, okay? So on the control plane, the analogy would be that the control plane is the brains of the Kubernetes cluster, okay? Normally, if you are using a cloud solution, you don't have to explicitly manage the control plane because that's done to you or by the cloud provider. So if you're running Kubernetes on the cloud, normally the cloud provider will manage the control plane. But if you are hosting Kubernetes on-prem, normally you are responsible for managing your control plane. Okay, so normally that is under your responsibility. Now, how should you manage it, ensure that it has high availability, and so on. Okay, but let's speak about the small components. Now, each and every of these components that constitutes the control plane. Okay. So the first one is the Cloud Controller Manager. So this small piece in here, okay? And this Cloud Controller Manager lets you link your Kubernetes cluster with your cloud provider's API, okay? What does this mean, okay? So normally Kubernetes aims to be cloud agnostic, okay? As we said before, okay? Tries to somewhat be platform agnostic, okay? But sometimes Kubernetes needs to interact with a cloud provider to create resources like load balancers, storage volumes, or even creating networking stuff like IPs for load balancers, okay? And this, of course, is only valid if you are using Kubernetes on the cloud. If you're not, then this component will, of course, normally not exist in your on-prem cluster. But the point is that normally you have to interact with those, with the cloud provider to create those resources, okay? As you progress in managing your cluster. And this component here is the one that is responsible to do that interaction with the cloud provider. If we come back, you will actually see here on this high-level picture or high-level overview that this component is the one that is connecting with the cloud provider, okay? And that's for the reason I just gave you, okay? Then the other one is the Kube API server, okay? And this one is the component that receives every request to the Kubernetes API, okay? Every request to the Kubernetes API comes through this service, okay, or this component, okay? Now, this component, of course, will expose the Kubernetes API, okay? And we will see this in practice once we use a tool called Kube Control. Okay, this Kube Control command line tool calls behind the scenes the Kubernetes API. And the Kubernetes API is somewhat, quote unquote, hidden behind this component. Okay, so every time we speak about calling the Kubernetes API, in reality, we are hitting this Kube API server, okay? And this component will be responsible for receiving this incoming HTTP request or API requests, generally speaking, and then doing whatever it needs to do to give you a response back, okay? The other component that we have is the controller manager, okay? This controller manager is very important because it is the component that is responsible to move your cluster into the desired state. Okay, what does this mean? So normally when you specify your Kubernetes cluster, you specify smaller components, as an example, a deployment. Okay, but regardless of the name, you specify how many instances of a given pod, or easily speaking, a container, you want to be running at any point in time. As an example, you tell your Kubernetes cluster, hey, I want to have 3 pods of Nginx running, okay, as an example. And then this component here will make sure that you always have 3 instances of Nginx up and running, okay? If one of them goes down, it's this component that is responsible for checking, hey, I specified my cluster, the desired state of my cluster is to have 3 Nginx instances running. I only have 2. What can I do to move the cluster from the current state, which is 2 Nginx instances, to the desired state, which is 3 Nginx instances, okay? And it does this by running some special thing called the control loop, or reconciliation loop, or controller loop, okay? Many names, but normally you would see it either as controller loop or reconciliation loop. And this reconciliation loop is the thing I just described. It's just going to check if whatever the desired state of my cluster is, I will, see if I'm on the desired state, and if not, I'll do some actions to move it to the desired state, okay? Now, in Kubernetes, we have a bunch of controllers, okay? We do not just have one controller, we have a bunch of controllers, and each controller is responsible for a specific action in this Kubernetes ecosystem. As an example, we have a node controller, okay, which is a controller that checks if I have X nodes up and running, okay. We also have a replication controller, okay, the example I just gave you, okay, to see if I have a specific number of pods up and running, okay. So you don't have only one controller, you have a bunch of controllers, and each controller has a specific responsibility on your cluster, okay. Next, we have the scheduler, okay? And as the name suggests, the scheduler is the component that is responsible to schedule things, namely, as an example, scheduling pods between the existing nodes, okay? So pods, we will speak about them in another video probably, but they are the basic unit of computation in Kubernetes, basic unit of deployment as well. And so they need to run somewhere, okay? That work needs to run somewhere. And it is the scheduler's job to understand which node which node is going to run this scheduler. And in order to take this decision, the scheduler has lots of things in consideration, okay? It has, as I told you, the individual resource requirements of each node, but also the collective resources from the cluster. You can always specify affinity and anti-affinity specifications, which is pretty much you can define rules to say I want specific pods to run on specific nodes and things like that. Okay, as also as I told you, hardware and some kind of policy constraints that you can also apply, and a bunch of other things. Okay, so the scheduler does not take a decision just for the sake of taking a decision. It has lots of factors in consideration, and based on those factors, it makes a decision. Okay. Last but not least, we have etcd. Okay, etcd is the database of Kubernetes. Okay, and pretty much etcd stores the information of the cluster. What kind of information it holds? Well, it holds information about metadata of the cluster, metadata of the nodes. For example, the name of the nodes, labels, any state or status that the node is on, the resources of the nodes, how much CPU, memory, and storage it has, and other things like that. Okay, as far as the node goes, but you also store in etcd pods, replica sets, deployments, and so on. Okay, but etcd is a key value store, if I'm not mistaken. It's high available, and so it's a backbone, let's say, of data in Kubernetes. Okay, everything is stored there. Okay. Well, that was all for the control plane. Now let's speak a bit about the worker nodes. Okay. The worker nodes, they have these components here. Okay. As I told you before, the control plane is the brains of the cluster, but the worker nodes, they are the muscle. Okay, the worker nodes are the nodes that will actually and effectively execute the workloads. Okay, so this is where the pods, if you will, the containers, are going to run. Okay, so they are very important. Okay, so let's speak about the components that a worker node or a node in Kubernetes has. Okay, first starting with the kubelet. Okay, the kubelet is an agent that runs on each worker node in Kubernetes, and it's responsible for managing the lifecycle of the containers or of the pods inside the node. Okay. Pretty much what kubelet does is it pulls data from the control plane via the API server that we just saw, and it will check for new changes. Okay. And if there are new changes, as an example, a new pod to run, then kubelet will orchestrate the process of running that pod. As an example, it will tell the CRI to pull a new Docker image, and then will orchestrate the process of having actually that pod up and running. Okay, so kubelet is that component. Okay, that component that is also close to the pods. Of course, kubeproxy is also one of the components, but this component is more close to network constraints or network policies, if you will. But kubeproxy is a network proxy that will ensure connectivity between the pods. Okay, pods within a node and also pods between nodes as well. Okay, but also will take care of routing in the pods. Okay, as an example, we will see further down the line when we speak about services, that services, they do load balancing, and kubeproxy is actually the one that does this load balancing magic behind the scenes. Okay, so anything that is network related, okay, either as an example, the pods having IPs or load balancing through services to the pods, anything like that, anything that is about routing and networking, those constraints, normally the kubeproxy takes care of them. Okay. Now, last but not least, the container runtime interface. Okay. So this is the component that is responsible to actually run the containers. Okay. This is the runtime. Okay. This is the actual, the meat. Okay. The thing that allows the containers to run, the pods to run. Okay. But we will speak about this in more detail in another video. There's some interesting considerations to do about the CRI, but pretty much, you know that containers, they need to run. They need to have a runtime to run on. And in this case, we have the CRI as a generic interface, let's say, that supports the execution of our pods. Okay. Now we can see again the diagram of our cluster architecture. Okay. So as you can see here, again, high-level overview. Okay, we have the Kube API server. As you can see, everything relies on this Kube API server. Okay, every call to the cluster state, to whatever, it's done to this Kube API server, which means that if we are managing it, we need to make sure that it's highly available and fault tolerant. Okay. Not only the Kube API server, but other components as etcd, for example. etcd database, if the data goes down, then your cluster state goes down, and then it's a mess. Okay. So there are a couple of components in Kubernetes that you need to have in consideration or under your eye, let's say, to guarantee high availability and fault tolerance. Okay. But as you can see, we have here the control plane. This is where, as I told you, the brains is. Okay. Then the scheduler will decide on which pod things will run. It will tell the Kube API server, hey, I've made a decision. Then somewhere down the line, this will get written into etcd. And then kubelet will pull Kube API server, like, hey, have you got anything new for me? Then, of course, a Kube API server serves itself from etcd and says, hey, yes, indeed, I have something for you to run. Then kubelet will say, hey, okay, I need this Docker image. It will tell the runtime, hey, runtime, download this Docker image. And then, of course, as we told, kubelet will manage the orchestrate the running of the pods themselves. One of the steps, of course, downloading the image from the repository itself. Okay. But as you can see, this right-hand side of the nodes, they rely on the left-hand side, okay, on the control plane, okay, so they are constantly pulling data, seeing if there's anything new to run and so on, okay. And hopefully, with this explanation, you can see that Kubernetes is not a single thing, it's a bunch of things that work together, and that together they achieve this concept of that we know that is container orchestration. Okay.